Welcome to lecture number 16 for ECE 320 Electronics 1, Fourier Transforms. Now, what we've been looking at in the previous lecture for the DC to DC converters is trying to calculate the ripple at the output. And in order to do that, I had to take a square wave and approximate it with a sine wave. There's a better, more accurate way to do it. That's Fourier Transforms. If you want a really accurate answer, use Fourier Transforms. It's a lot of work, but you'll get the actual answer. The other alternative is do what we did in the last lecture, make an approximation, and then use CircuitLab to fine-tune it. Now, the Fourier Transforms, that's using the concepts of superposition and phasors. Phasor analysis says that in order to analyze a circuit with at DC, all I need are real numbers. If I want to analyze AC circuits, however, I need to use complex numbers. And if I'm willing to use complex numbers, then AC is just like DC. The phasor conversion from voltages and impedances to complex numbers is if I have a sine wave, the real part is cosine minus j is sine. That's the beauty of complex numbers. I can represent both the sine and the cosine with a single number. If I do that, then impedances become, resistors don't change, inductors become j omega L, capacitors become whatever j omega C. So if I have an AC circuit with voltage sources and capacitors, resistors, inductors, I'll have a circuit with a bunch of complex numbers in it. The analysis is exactly like it was at DC. I can use voltage nodes, current loops, voltage division, whatever you like. Whatever worked at DC works just fine at AC, except now you're going to get complex numbers. That's phasors. The second half for Fourier transform is superposition. Now, circuits with resistors, capacitors, inductors are linear. What that means is that if I have a function of A plus B that's equal to f of A plus f of B, that's the definition of linear. Where that applies to Fourier transforms is suppose I have two separate inputs, something at 1 kilohertz and something at 2 kilohertz. I can treat that as two separate problems. Analyze the circuit at 1 kilohertz, analyze the circuit at 2 kilohertz, add the two answers together, and that's exactly the same thing you'll get if I have the circuit with two frequencies feeding it. The advantage of that is if I have a known frequency like 1 kilohertz, I can do phasor analysis at that one frequency. Change the frequency, I need to analyze a different circuit. So as long as I only have a single frequency, I can do phasor analysis. This changes the problem where you have multiple frequencies into one I can solve. What Fourier transforms do is that if you have a signal that is not made up of sine waves, like a square wave, I can convert it into a signal that is made up of sine waves. That allows me to use phasor analysis and superposition. Each one of these will be a different frequency. Add them all up, I'll get the original square wave. So the first step with using Fourier transform is given a signal, convert it to a bunch of sine waves. What the Fourier transform says that if my signal is periodic, that's what this says, x of t plus the period is x of t, so the signal just repeats over and over again. If that's true, then your signal could be expressed in terms of cosines and sine waves, where each one is a harmonic of the fundamental. Equals is a powerful symbol. It means these are exactly the same. Going right to left, what that means is if I add up a whole bunch of sine waves that are periodic, the answer is periodic. And that's kind of like a no-brainer, yeah, sure. The interesting part is going left to right. If my signal is periodic, it has harmonics. To find the Fourier coefficients, there's a couple ways to do that. One approach is to note that all sine waves are orthogonal, meaning that if I have sine times cosine, the answer will always be 0. Sine times sine is also 0 unless a equals b. Then I get sine squared. The average of sine squared is a half. The average of cosine, a times cosine b, is also 0, except when a equals b. Then I get cosine squared, and again the average is a half. So what that means is that if my signal is made up of a bunch of sines and cosines, I can pull off the different components. Just take the average, and that'll give you the DC term. Take your signal, hit it by a cosine, and all the terms will average out to 0 except the n omega naught. That'll average out to a half. To find the amplitude, then just multiply by 2 to cancel the half. Likewise for sine. So this will find all the Fourier coefficients. To check that algorithm, start with a function where you know what the answer is. Suppose I had x of t contains three terms, a DC term, something at 1 radian per second, something at 2. To find the Fourier coefficients, I would just use the previous equations. The average is a0, and that's one that works. The average of x times cosine will be 3. That matches up. X times sine is 0. There is no sine of t terms. X times cosine 2t is 0. There's no cosine 2t term. X times sine of 2t is 4. So that pulls off the coefficients just fine. That works when I have a function where I know what the answer is. Now, kind of a leap of faith is if I have a function where I don't know what it is. There's also a shortcut. There's a complex Fourier transform. If you don't mind complex numbers, I can do this all in one shot. Just take x times e to the minus jt, and the real part will be cosine, minus j will be sine. So here's where the leap of faith comes in. That worked for a function where I knew what the answer was. Let's take a function where I don't know what the answer is, meaning the square wave that we had last time. This is your buck converter, 40% on at 20 volts, 60% off at minus 0.7. V1 is not a sine wave. Find the Fourier transform of it. Find a bunch of sine waves that do add up to V1. So the previous solution that we did was approximate this with two terms, a DC term and 1 kilohertz term. That's a little bit wrong. The correct way is to use Fourier transforms. To get the terms, the average of x is your DC term. Here's the first harmonic at 1 kilohertz, cosine and sine. Second harmonic, cosine and sine. Third harmonic, 3 kilohertz, cosine sine. Fourth harmonic, 4 kilohertz, cosine sine. What that means is that here's your function. And t, I just did a change in variable, so the period is 2 pi. The coefficients will stay the same. But this says this is what v of t is at the DC term, first harmonic, second, third, fourth. Now that I have the input in terms of sine waves, I can use superposition and phasor analysis and analyze this as 5 separate problems. So to do that, I'll first start at DC. Here's the DC term. If the input is DC, this part of the circuit doesn't matter. All the part on the right cares about is I got 7.57 volts at DC for V1. How I got it, I don't care. All it cares about it is the voltage. I can now find V2 by using voltage division and get 6.58 volts. Next, solve the circuit at 1 kilohertz. At 1 kilohertz, V1 is 2.87 minus J 11.9. The inductor becomes J omega L. Capacitor becomes 1 over J omega C. These two terms get added in parallel. And then I have voltage division. Do that times V1, and I get V2. So that's the 1 kilohertz component of V2. Next, repeat at 2 kilohertz. Here's the input at 2 kilohertz. The inductor becomes J omega L. Capacitor becomes 1 over J omega C. These get added in parallel. Do voltage division, and I get V2. Next, repeat at 3 kilohertz. And then repeat at 4 kilohertz. Put it all together, I now have V2 of t. I've got a DC term, 1 kilohertz, 2 kilohertz, 3 kilohertz, 4 kilohertz, and so on out to infinity. That will actually match up with the circuit lab results. A couple things to note. In theory, Fourier transform has to go out to infinity. In practice, the terms go to 0 fairly quickly. And this is a visit by Momo. Say hi to Momo. In practice, the terms go to 0 fairly quickly, so I only have to consider a couple terms in the Fourier series, and I'll have a pretty good approximation of the actual answer. Next, you can use the Fourier transform to calculate the explicit form of V2 of t. The Fourier transforms are much more accurate than what we did last lecture. However, as you notice, it's a lot more work. I have to find the frequency component of the input. I have to analyze the circuit, add a bunch of different frequencies, find the output of a bunch of different frequencies. You can do it, but it is a ton more work. But you can do it. Likewise, that's about all we're going to do for Fourier transforms in this class. The main thing to get out of it is when we did the buck converter and analyzed it last lecture, Our answers were slightly wrong. The reason they're wrong is I didn't find the first harmonic correctly. This is actually the first harmonic in V1 of t. It's not actually 20.7 volts peak to peak. If I use this term, I'd have slightly more accurate answers. Use the whole Fourier series, I'll have even more accurate answers for a lot more work. And that's lecture number 16, Fourier Transforms for ECE 320 Electronics 1.